Hello and welcome to this very quick and basic intro to the maths of spin. So the goal of this video is not to introduce you to the basic physical effects of spin, but rather to the mathematics behind it. So what are spin operators? How do they work? How are they represented by the Pauli matrices? How do the Pauli matrices work? We're going to have a look at a few basic examples of the Pauli matrices in action, and then in the end the goal is to understand one basic and easy but also very fundamental physical effect. Namely, we're asking ourselves what happens to a spin right particle which is located in a magnetic Z field, so a magnetic field that is pointed in the Z direction. So maybe you might know, classically what we expect is that the spin will start precessing around the Z axis, right? So if this is my Z direction, this is my spin, the spin will start doing this kind of motion. So it's precessing around the Z axis. Classically, this is quite clear. But the goal is to understand quantum mechanically why this happens using the Pauli matrices and the Schrödinger equation, basically. Okay, so let's start with the basics. So the spin operator is basically a three-dimensional vector. So the spin operator is the spin x operator, the spin y operator, and the spin z operator. So we've got three directions of spin. And as always in quantum mechanics, we cannot measure all of them at the same time. This is shown by the commutator relations. So for example, the commutator of spin x and spin y is I, so the imaginary unit I, times h bar times the spin z operator, which is non-zero in general. That means we cannot measure Sx and Sy at the same time. So in general, always when the commutator of two operators is not zero, we cannot measure these two at the same time with arbitrary accuracy, which is the uncertainty principle, right? Okay, so one more example of a commutator relation would be S squared and Sz, and this commutator actually is zero, so these two operators do commute, which means that we can simultaneously, with arbitrary accuracy, measure S squared and the Z component of the spin vector. For example, there are many more commutator relations which then tell us what can be measured at the same time. But let's now talk about the Pauli matrices. Because as you can see, the components of the spin operator, so Sx, Sy, and Sz, are operators themselves. And because they're operators, we can represent them using matrices, because matrices are operators, right? So if you have a matrix and multiply it with a vector, then you'll get a new vector, because the matrix is operating on the vector and spits out a new vector. So this is why there are the Pauli matrices, which are representations of these spin x, y, and z operators. So, for example, the spin x operator is h bar over 2 times a matrix. This matrix is 0, 1, 1, 0, and this matrix is called the Pauli X matrix. Similarly, the sy spin operator is again h bar over 2 times the Pauli Y matrix, which is O minus I, and O. Pauli Y matrix. And the spin Z operator is again h bar over 2 times the Pauli Z matrix, which is 1, 0, 0, minus 1. Pauli Z. Okay, so these are the matrix representations of the three spin operators in the three spatial directions. Now the question is, what are the eigenstates or the eigenvectors of these matrices? So if you're looking, for example, for the eigenvectors of this matrix, so the two vectors in that case which are not really touched by the matrix, right? So eigenvectors are vectors which are maybe stretched by the matrix but not altered in direction. So the eigenvectors of the Sz matrix, for example, are 1, 0 and 0, 1. We're going to prove that in a second. And these vectors will then be called the spin up and spin down, right? So just as an example, the eigenstates of the Sz operator are the following two. So 1, 0, and this is what we call spin up, and many people use a sign like this, spin up, right? And another eigenstate of SZ is spin down, which looks like this, and spin down in the vector notation is O1. Okay, so let's quickly prove this. So why are these the eigenstates? Reminder, eigenstate or eigenvector means that if you multiply the matrix by this vector, the vector is unchanged apart from some coefficients, but the direction won't change. Okay, so let's see what happens when we apply SZ, so the SZ operator, to the state spin up. So this operator should not change the state, it's merely allowed to stretch the state but not to alter its direction in the vector space. So SZ is this matrix, so h bar over 2 times O1, O minus 1, and spin up is the vector 1, 0. If you multiply these two together, what you get is, well, 1, 0 again, and 1, 0 is nothing else but spin up. Okay? Or to put it in another way, h bar times 1 over 2 times spin up. So, indeed, spin up or 1, 0 is an eigenstate of the Pauli SZ matrix, or of the spin operator SZ, because applying SZ to spin up yields something which is spin up times some number which we don't really care about. Same thing for spin down. So if you apply the SZ operator to the spin down state, what you get is some number, in that case h bar times minus 1/2 times the spin down state again. So the spin down state indeed is also an eigenstate of the SZ operator. And a general rule maybe is if you apply the SZ operator to some quantum state psi, then what you get is h bar times the spin m number, which in this case was 1 or 1/2 or minus 1/2 times, well, the state again, right? So in that case, we were looking at spin 1/2 systems. Spin 1/2 systems allow m to be 1/2 or minus 1/2. If we were looking at spin 1 systems, this m number could be minus 1, 0, or 1. For spin 2 systems, minus 2, minus 1, 0, 1, 2, and so on. And this is the rule, what the eigenvalues are of the respective spin states. Okay, let's go on to one more example. But first, we need to introduce some further spin states. So we also we already talked about the spin up and spin down states. So what's missing? There's also a spin left state, a spin left state, a spin right state, a spin which is pointing towards you, and a spin which is pointing away from you. And these 4 spins can also be represented using vectors as follows. Right, so these are now basically the eigenvectors of the Sx and Sy spin operators. So spin right is 1 over root 2 times 1, 1. Spin left is 1 over root 2, 1, minus 1. Spin pointing towards us is 1 over root 2, 1 I, and spin pointing away from us in this convention is 1 over root 2 times 1 minus I. So one more example before we go on, looking at what happens to spin in a magnetic field. But let's just have a look to understand this even better. What happens when you apply the SZ operator to an eigenstate which is not an eigenstate of the SZ operator? So for example, what happens by applying SZ to the spin right state? So the spin Z operator is just able to measure spin up or spin down. So what happens when you try to measure a spin which is actually pointing to the right, which is a perfect like superposition of up and down? Well, let's see. That is quite easy mathematically. So we know that the spin Z operator is this matrix, right? So spin Z is h bar over 2 times O1, O1, O minus 1. And the spin right state is this one, so 1 over root 2, 1, 1. If you calculate this, what you get is h bar over 2 root 2, and then 1 minus 1. Okay. what we now can see is that 1 minus 1 is actually a superposition of two things we know. 1 minus 1 is nothing but 1, 0, minus 0, 1. 1, 0 is spin up, 0, 1 is spin down. So this is some coefficients which are not so important, times spin up minus spin down. Okay, that makes sense. So if you try to measure a spin right particle with an operator which can only measure spin up or spin down, what you get is an equal distribution of spin up and spin down, because the spin right state is an equal superposition of spin up and spin down. This is why what we get is spin up half of the time and spin down half of the time. If I chose this state to be a state which is spin right but with a little tilt to spin up, then what this SZ operator will give us is spin up a bit more often than spin down. So these operators can only measure in the direction which this index represents. Okay, then let's go to the one very fundamental application I talked about before, namely a spin in a magnetic Z field. Okay, let's talk about what we expect classically for a few seconds. So again, we have a magnetic field in the Z direction, right? So this is Z, and then there is a spin right particle in this field, so a particle like this. What do we expect from this? Well, this is like in classical mechanics when you have an angular momentum, so a spinning top, for example, on which a torque is exerted. That will always mean there will be a precession, so the the angular momentum will start precessing, so it will start spinning around the axis of the force which is exerting the torque. So this is like, I don't know, maybe you've seen this experiment, having a rope and the tire of a bike which is spinning very slowly, very fast, sorry. Then this tire will start doing this motion around the rope. This is a precession. And the same thing is what we expect from this. So we expect this spin right to eventually become a spin. This is pointing, a spin which is pointing towards us, then a spin which is pointing to the left, then a spin which is pointing away from us, and then the spin right again. So what we expect classically is a precession motion. So let's now see if we're able to derive this from the fundamental things we've learned now and the Schrödinger equation. So first, to describe quantum states, what we need is the Hamiltonian, right? So Hamiltonians are nothing but energy, so we have to find out what the energy of the system is. And the energy of a magnetic dipole moment in a magnetic field is always minus the dipole moment operator times, so dot product, magnetic field. So this is the Hamiltonian. Now let's see what this can be simplified to. So a few things we have to plug in is, so first thing is, we know that the magnetic dipole moment of a spin is minus the Landé G factor, which is about 2, so just a coefficient, times the Bohr magneton, which is also just a number, divided by h bar, which is also just a number, multiplied with the spin operator, in this case in the z direction. And of course our magnetic field is pointing in the z direction, so this dot product can be simplified to a simple multiplication. And what we get is, well, this minus and this minus cancel out, so we get G factor times Bohr magneton times magnetic field in z direction divided by h bar times spin z operator. Now what we know is that the spin z operator is nothing but h bar over 2 times this Pauli matrix, which was 1, 0, 0, minus 1, right? So this h bar cancels out with this one, and we are left with G factor, Bohr magneton, magnetic field flux density divided by 2, this is the 2 from over there, times the Pauli Z matrix, so 1, 0, 0, minus 1. And one last step to simplify this is to pull these coefficients into the matrix. So the Hamiltonian is given by GS Bohr magneton magnetic field divided by 2, 0, 0, and minus G factor Bohr magneton magnetic field divided by 2. So this is the Hamiltonian we'll use now to find out if the spin is really precessing as we are expecting classically. So one thing we need is the time-independent Schrödinger equation. This equation describes the time evolution of quantum states in a time-independent surrounding. In this case, our magnetic field is time-independent, so it's not changing over time. So we can use this time-independent equation, which is given by IH bar times quantum state dot, so differentiated with respect to time, is equal to Hamiltonian quantum state. In other words, by dividing by h bar times I, we get that psi dot is minus, so dividing by I is like multiplying with minus I Hamiltonian divided by h bar psi. This is a basically very simple differential equation, which tells us that in general, the state of the system at the time t is the same as the initial state, so the state at time 0 times e to the minus I Hamiltonian divided by h bar times the time t. Okay, in this case, our initial state, psi of 0, is spin right. So the question is, what does a spin right particle do in a magnetic field? So initial state, psi of 0, is spin right. So this is a spin right in our case. And what about this? Well, we know that the Hamiltonian is this matrix. So what we have to do is pull minus I t times h bar into the matrix, which leads us to the following expression. So I've done nothing but pull these factors, so minus I t divided by h bar, into the Hamiltonian matrix we had above, and exponentiated the whole thing with e, and times psi of 0 is spin right. So now what is e to the power of a matrix? Well, since the matrix is diagonal, this is quite easy. We can just pull the exponential into the matrix, right? So this is nothing but a matrix with components e to the minus this, 0, 0, and e to the plus this. So this works because the matrix is diagonal. So I've now pulled in the e to the in the matrix times spin right. So this is now describing the evolution of the quantum state we were looking at. So this is describing the evolution of the spin right state in a magnetic Z field. So let's find out if this really describes the precession we'd like it to describe. So let's start off by checking if psi of 0, so the initial state, is really the thing we'd like it to be, so if that really is spin right. So psi of 0 means plugging in 0 for every t, okay? So plugging in 0 for every t yields e to the 0, which is 1, 0, 0, e to the 0 is 1 again, times spin right. So psi of 0 is the identity matrix times spin right, which is spin right, which makes sense. So the state we start in is actually spin right as we would like it to be. Okay, so what happens at a time t1, which is larger than 0? Let me just choose t1 in a way that the numbers are beautiful. So t1 can be anything. In my case, I would like t1 to be such a number that this exponent becomes e to the minus I pi over 4, right? So that is allowed. I promise this will yield nice results in the end. So definitely there is a positive value of t such that this whole exponent will be pi over 4 times the I at the start, right? So there's no problem in choosing t1 so that this works. 0, 0, and if this is e to the minus I pi over 4, the bottom right one will be e to the plus I pi over 4 times the initial state, so times the spin right. And we know the vector representation of spin right is 1 over root 2 times 1, 1. So we have to multiply this vector by this matrix, which gives us 1 over root 2 times e to the minus I pi over 4 and e to the I pi over 4. Okay, now why did I say this is beautiful? This does not look like anything we know. But there's one thing which is good about quantum mechanics, and this one good thing is that global phases do not matter. So if you have a quantum mechanical state like psi, and you multiply this by some global phase e to the I phi, then this will not change the physical nature of the state. It will just change the imaginary phase, but it won't change the state. So I can always multiply states with e to the I something. Okay, so this state is equivalent to this state multiplied by e to the I pi over 4. Since multiplying with phases is always allowed. What this will give us is 1 over root 2 times, well, e to the I pi over 4 times e to the minus I pi over 4 is just 1, and this gives us e to the I pi over 2, which is I. And this state is well known. This state was the state we called dot before, right? Just to remind you, this state, 1 over root 2 times 1i, is the state we called dot before. So indeed, there seems to be some kind of precession happening. We started in the spin right state, and we ended up after a certain amount of time in the spin pointing towards us state. And you can do the rest yourself if you want to. So if you do this at twice t1, so again t1 later, what you get is spin left state. If you do it after 3t1, what you get is the spin pointing away from you. And what you get after 4t1, what you get is spin right again. And this is the proof that indeed these quantum calculations yield exactly the result we would expect in classical mechanics, namely a precession of the spin around the axis of the magnetic field. So it starts at right, goes to pointing towards you, goes to left, goes to pointing away, and goes to pointing right again. So this is how to derive this basic spin precession in the spin algebra picture. So as like a last point I'd like to do, let's calculate the frequency of this precession. So how fast is this spin precessing around the z-axis? Well, each of these steps was a quarter of a revolution, right? So we started in spin right, that was when there was a 1 in the matrix, and then after a while there was a I pi over 4 in the matrix, that was spin towards us. Then after some time there was an I pi over 2 in this matrix, that meant spin left. Then after some time there was an I 3 pi over 4 in the matrix, that meant spin down. And then after some time there was e to the minus I pi times 1 in the matrix. That was when we did one full revolution, right? So one full cycle has passed when we get an exponent of plus or minus e to the I, or an exponent of I times pi in the matrix. So if this thing here is I times pi, we know that one cycle has passed. which will then directly yield the time of one cycle, right? So this thing has to be I times pi. So I times g factor Bohr magneton magnetic field flux density divided by 2h bar times t, which is what we have in the exponent. This has to be I times pi in order to have one full cycle. We can solve this for the time t. T is then 2 pi h bar divided by lambda g factor times Bohr magneton times magnetic z field. So this is the time it takes for one cycle of precession. That means the frequency, which is often called Larmor frequency, so the frequency of a spin particle precessing in a magnetic field of strength Bz, is, as always, 2 pi over the time, which is the definition of frequency. So 2 pi over this thing, which is g factor times Bohr magneton divided by h bar times magnetic field flux density. So this is the so-called Larmor frequency of spin precessing in a magnetic field, and this is the so-called gyromagnetic ratio, which is often called gamma, so we can just write this frequency as gamma times magnetic field. So what we've learned now, what we've derived now from basic spin mechanics, so we did not use anything weird. We used the Pauli matrices, we used the fact that the magnetic dipole moment is given by this, and we used the very basic stationary or time-independent Schrödinger equation. What we got is the well-known formula for the Larmor frequency. So the Larmor frequency of a spin precessing in a magnetic field is gyromagnetic ratio times magnetic field strength. And this gyromagnetic ratio is given by, sometimes there is a minus, sometimes there's a plus, lambda g factor, which is about 2 for the electron, times Bohr magneton divided by h bar. So loads of fundamental constants appearing in these derivations. So that was all. I hope I could help you understand a few more basics of spin and spin dynamics. If there are any questions, please put them in the comments. If you have any recommendations for upcoming videos, please also put them in the comments. And if you have been, thanks for watching.